We're going to look at some basic things right now then that are important that factor into that 120/75. What are some of those variables that lead to somebody having a blood pressure of a specific number? And then we'll talk a little bit about hypertension and why blood pressure in some individuals can be higher than others and what can be done about that. Now, the thing that probably we can kind of, there's another thing that's not on here, and that's the length of the blood vessels. All these things play a role in determining what our blood pressure is. The thing that's not on here is the length of our blood vessels. The length of our blood vessels is not going to change from day to day. The distance, if we were to measure them, is not going to change. So that's really, we're not even going to factor that in. If we were to rank these, probably the thing that really in a healthy individual is not going to play a huge role in determining our blood pressure is viscosity, the thickness of that blood. In other words, how many plasma proteins and how many red blood cells. That's typically not going to change much on a day-to-day basis. However, these three things here, cardiac output, blood volume, and peripheral resistance, those do play more of a role in the day-to-day management and determination of what our blood pressure is, even minute to minute. So let's look at these one at a time here. Cardiac output, we'll abbreviate it CO, is a product of the heart rate and what we call the stroke volume. So it's two variables. Heart rate is the number of times the heart beats per minute. So beats per minute. And on average, we'll just say it's 70. It'll make our math much simpler. Let's say the heart beats 70 times a minute. That means blood is leaving the left ventricle 70 times every minute. Not leaving the right ventricle 70 times every minute too, but we know that's just going to the lungs. Stroke volume. That refers to the volume of blood that's ejected from the left ventricle, or the right, it should be the same. The amount of blood ejected from the ventricle every time the heart beats. And so we measure that as milliliters per beat. If you've ever taken chemistry, you've probably set up your equations in proportions like this so that you can very easily cancel out like units. So if we know that the volume ejected from the heart every time the heart beats is 70 milliliters, we can figure out how much blood is ejected from the heart every minute. So cardiac output is measured as milliliters per minute. 400 multiplied. Not added. 4,900 milliliters a minute. 4.9 liters a minute. Which means that if you have about 5 liters of blood in your body, your blood is circulating once every minute. This does factor into your blood pressure. Not so much volume, but heart rate. So if our heart rate goes up, assuming that cardiac output, stroke volume is the same, then cardiac output goes up, doesn't it? If we kept this at 70 and changed this to 100 beats a minute, what's our new cardiac output? 100 times 70 is 7,000. Now we're at 7,000 milliliters per minute. Cardiac output increases. So basically, when cardiac output increases, blood pressure increases. When cardiac output decreases, blood pressure decreases. Now, there's a couple intermediate steps I'm skipping because it relates to resistance. But this is if we looked at cardiac output and kept everything else the same, this is what would happen to blood pressure. Now, I won't ask you on the exam, I won't say, if cardiac output goes up and stroke volume goes down, what's going to happen to blood pressure? I won't do that unless I gave you specific numbers. And I won't even do that because we're not really getting into the depth of this that I want for this semester. But if I said cardiac output goes up, be able to tell me what happens to blood pressure. Or if heart rate goes up and stroke volume stays the same, how would that affect blood pressure? Well, if heart rate goes up, stroke volume stays the same, that will cause cardiac output to go up, which means that blood pressure goes up. Okay? Now, blood volume. This is referring to obviously the volume of water in the blood, specifically the blood plasma. And the body has a variety of mechanisms to help regulate the volume of water in the blood, whether there's too much or too little. Again, homeostasis. So if we increase the blood volume, then blood pressure goes up. The more water we add to the plasma, the more pressure that there will be. If we decrease the blood volume, then blood pressure should go down. Now again, that's keeping cardiac output, peripheral resistance, and viscosity the same. That's the way I want you to look at these for now. When you get into nursing or your other courses that you're taking, whatever, advanced courses, they may ask you to look at all of these factors at once and determine what happens with blood pressure. But for me, what I want you to be able to do is, looking at these individually, assuming everything else is static, how is this going to affect blood pressure? Well, the thing that probably has the greatest effect on blood pressure from a minute-to-minute standpoint is peripheral resistance. And that has to do with the diameter of the blood vessels. And this relates to vasoconstriction and dilation. This is really the day-to-day, the quickest way for our body to adjust and regulate blood pressure. Is change the diameter of those vessels. And if we change the diameter of the vessel, we either are increasing or decreasing the friction created. And it's the friction of the blood moving against the walls of the vessel that creates the resistance. Resistance meaning harder to move. And if we want to keep blood moving at the same rate, then we have to have a higher pressure to force that blood through those vessels. Basically what happens is if you increase the diameter of the vessel, then you decrease the resistance. Meaning blood flows through the vessel with less friction when it's a larger diameter. If you decrease the diameter, in other words, you're causing constriction of the vessel, then you increase the resistance. There's more friction now. And as a result, you're going to increase the blood pressure. So when we talk about resistance here and pressures going up or down, we're talking about the same volume of blood going to those particular areas. So this is what plays the biggest role in most day-to-day blood pressure maintenance, minute-to-minute blood pressure maintenance. What are the receptors called that monitor blood pressure? The baroreceptors. Baro means pressure. A barometer, a barometer, measures atmospheric pressure. Aortic arch and the carotid sinuses. So here is the right and left common carotids. They branch into the internal and external carotids. Right here in this space here, that's the carotid sinus. In the walls of those carotid sinuses, there are stretch receptors. They're mechanoreceptors. They respond to stretching of the walls of these arteries. And then if we draw the aorta in here, aortic arch, here's your brachiocephalic trunk, left common carotid, left subclavian. Right here, kind of in the arch, are going to be pressure receptors as well. All of these pressure receptors are connected to cranial nerve 9, the glossopharyngeal nerve. What brainstem structure is the glossopharyngeal nerve connected to? Where do those sensory nerve fibers end? The medulla oblongata. Cranial nerves 9, 10, 11, and 12 are all attached to the medulla. And what structures do we have in the medulla that relate to heart rate and vasomotion? We got the vasomotor center that controls constriction and dilation, and we also have the center that works to increase the heart rate, and the cardioinhibitory center that works to decrease the heart rate. So we have a heart rate center, and we have a vasomotor center. Well, these glossopharyngeal nerves go to the medulla. Medulla then decides what to do and sends signals to the heart. One of the things that can happen is that we can decrease the heart rate. We know that if we decrease the heart rate, what does that do to cardiac output? Assuming stroke volume is the same. We decrease the cardiac output, and what happens when we decrease cardiac output? Blood pressure goes down. So when blood pressure gets too high, these baroreceptors send signals via the glossopharyngeal nerve to the medulla. The cardiac center can decrease the heart rate, and the vasomotor center can decrease the resistance in vessels, which then does what to blood pressure? Cause it to go down. By the way, what nerve would come from the medulla that tells the heart rate to decrease? Cranial nerve 10, the vagus nerve. Leaves the medulla, goes to the SA node, causes the heart rate to decrease. Decreasing the heart rate decreases cardiac output, which decreases blood pressure. And then we have various other sympathetic nerves that will either increase or decrease the stimulation to cause vasoconstriction or vasodilation.
In a person that's healthy and has regular blood pressure, when would this happen? Like when you're exercising or something?
Well, when you exercise, what happens is this changes everything. Because the body's now looking at input from your chemoreceptors, which are monitoring the different levels of carbon dioxide in your blood. They're monitoring the stimulation of various proprioceptors in your joints and in your bones. And so that changes everything. But just day-to-day sitting here, if you stand up too quickly, sometimes you feel a little faint. Okay, that's because your blood pressure hasn't kicked in yet. Your heart rate hasn't increased yet to maintain the proper flow of blood to the brain. Okay, so day-to-day activities, this is happening all the time. Standing up, sitting down, laying down, moving around, whatever, all the time.